Okay, welcome everybody to Session 2A. This is the special track on continuous planning, which was organised by Brian Williams and me, and we have 3 papers in this session. So our first paper, if we're ready, will be presented by Johannes Lohr, and that's a planning-based framework for controlling hybrid systems.
Thanks very much. Okay, hello everybody. I will talk about quite an interesting field I've been working on together with Patrick and Thomas and Bernard Nebel. It's about the utilization of a planning algorithm for the control of real-world hybrid systems. For instance, the motion of a car or the attitude dynamics of a satellite or something that can be modeled by the use of differential equations. Therefore, we put a planner into such a construction with a hybrid system for the development of a planning-based framework for controlling hybrid systems. Let me give you a short outline of my presentation. I will talk about the motivation firstly, why do we want to use planning for hybrid system control. Then I will talk about how we can get from the continuous dynamics of the hybrid system to a domain model where we can actually plan on. Then I will talk about our approach, the domain predictive control approach, the architecture with the slip structure. I will show some exemplary simulation results and discuss the whole approach and a short bottle on actually current work. Okay, we're doing this research together with the space company EADS Asteron, and I have myself a space engineering background. And we have learned this morning in my talk that, for instance, landing of landers is a very challenging task for spacecraft. What you see here is the lunar lander and the extra mission of ESA, and both spacecraft have to reach the goals in the absence of permanent communication links, but in the presence of failures and uncertainties. And there can happen a lot of things. For instance, there could be turbulences here in the atmosphere of Mars, so that we are currently in a state where we didn't expect to be, for instance. Or at the landing site, there's a crater, so that we cannot land where we want to land. Or a system failure occurs here, so that the thruster is faulty, for instance. Normally, in such a case, the mission could be lost because we cannot interact from Earth with the spacecraft to find a solution. That's why we want to find a framework where we can connect the planning algorithm with a hybrid system, so that the planning algorithm start thinking what is the best next suitable sequence of actions if we provide some load information, for instance, the safe landing at the desired landing site, and the planner receives the actual current hybrid system state. Then again, the planner starts thinking what's the best next suitable actions to guide the hybrid system into a direction we want, into a state satisfying suitable condition. So this is the key idea. And if we want to develop such a framework, we have to focus on 3 main aspects here. First of all, we have to handle a hybrid system. That basically means we have a system with continuous dynamics, and which are captured by numerical state variables, and we have additional Boolean state variables, which define the mode of the hybrid system. Additionally, we want to make our spacecraft more autonomous. That means we have to do this computation on board. That means we have to reduce the computational effort as much as we can, because the computational resources, especially on spacecraft, are strictly limited. Then we want to make sure that we generate our decisions very quickly. So we have some real-time aspects here. And finally, we want to be reactive to exogenous events that are events which are not planned, which simply occur in the environment. For instance, if there occurs some obstacles in the environment, or if there occurs a system failure, we want to react on the system failure as well. So let's start in the beginning. What's a hybrid system? I think most of you are aware of that. but let's briefly go through the equation here. The hybrid system is basically a set of differential equations having a numerical state vector xn, and for numerical containing all the numerical information, for instance the current position or the current velocity of car or the current angular rate of the satellite. And additionally we have a logical state vector here defining the node of the hybrid system. This could be, for instance, the current actuator configuration or the current system dynamics that we are using underlying control feedback loops. And the planning task is now to find an input signal U. So if we want to change the numerical state variables here, we have to apply an external force, for instance, next to the signal, for instance, a force or torque. And the planning task is now to find a sequence of forces or torques or an external input signal U within a time window TA to T that we transform the initial state into a state satisfying some load conditions. So this, again, this is the idea. We want to use a planner to generate an input signal which then goes into the hybrid system and leads the hybrid system into a state satisfying some load conditions. Therefore, we basically have a three-step process. First of all, we anticipate some input fragments, for instance, the actuation of a thruster or a whole braking maneuver or something that we can imagine what could be useful to solve the control task. In the second step then, we solve the differential equations of the hybrid system, and in the third step, we generate the planning action here. Having preconditions, having a duration, and effects. We store the information about the homogeneous solution here, the state transition matrix, defined by this matrix exponential function here, and the inhomogeneous term, which is basically the impact of the anticipated input fragment, obtained here by the convolution of the dynamics with this anticipated input fragment, and finally the input fragment itself. The planner is now able to predict the future numerical state just by the evaluation of this equation here. So we are currently in a current state with a current position and current velocity, for instance, and we know the future numerical state just by the multiplication of the current numerical state with the state transition matrix here, and with the addition of the inhomogeneous term. So this is a very simple equation we can express in a planning language, while we do this complex computation above here in a pre-processing step when we set up the domain. So this is how a planner can predict future numerical states. A set of leaf actions embodies now our domain model. The planning problem is still defined by the initial state where we currently are and the goal state where we want to be. And if we look at this right graph here, these are the numerical states and this is the time into the future. So the planner can start stringing together actions and predicting future states until he has found a state which satisfies the goal conditions. Thereby generating a sequence of actions which can be translated back into the real world, into an input signal which will guide our hybrid system into a state satisfying the goal conditions. So this is the idea. So let's talk about the domain predictive control architecture, but before we go into detail there, let's remember the key aspect. We want to reduce the computational effort and complexity of this resulting planning problems. And we want to make sure that we generate our decisions very quickly. Basically, we are using their methods from model predictive control. So if we have a decision tree like this one here, so we are in an initial state and we start exploring child nodes by applying all available actions we have, and we start exploring the decision tree here until we have found a state satisfying the goal condition. Then the lambda would probably be crashed because we don't have the time to search within an almost infinite state space. That's why we use a prediction horizon. So we only plan to a certain depth of the decision tree. For instance, here 4 steps. And additionally, we limit the number of states to be explored by the planning algorithm. The planner will then return a state which is good regarding heuristic information. And the state does not necessarily has to lie on the path towards the goal states, because in the second step, we just apply a subsequence of actions towards the state which was good regarding the heuristic information of the planning algorithm, and then we recede the horizon, or the horizon is receded, and we start exploring this subtree again. Again, we apply a subsequence of actions towards the state with best heuristic information. Again, the horizon is receded until we have spotted some states which are satisfying our goal conditions. And then we have found a solution. Of course, if we increase the number of states to be explored by the planning algorithm, and if we increase the prediction horizon, then we will reduce the possibility to end up in a dead end. But this is finally simply defined by our computational resources we have available. So this was the autonomy aspect, and let's now talk about exogenous events and how we can handle obstacles in the environment or system failures, for instance. In domain predictive control, let's imagine the lander receives some new information about the environment or about the system itself. At each time we replan here, we can update the planning problem and the domain model. For instance, in the planning problem, the current initial state, if we are suddenly in a state where we didn't expect to be, this can easily happen if in the real world there are some dynamics which we have not modeled in the domain model. So we can update the initial state. Or we can update the goal information, for instance, if the landing site has changed. At the other hand, we can update the domain model itself. If there is a system failure, we can at least try to solve the control problem here, or the planning problem, by the use of the remaining feasible actions. So this is how we can try to increase the failure tolerance of our hybrid system. And this finally is the domain predictive control architecture. Let's briefly go through the loop here. A user or an external system defines or provides some goal information S star. This goes into the planning problem. And we receive the current hybrid system state here. And the planner starts now predicting future states, generating a plan on the basis of the domain model is available here. This plan goes into the interpreter here and will interpret it into a numerical input signal, for instance, a sequence of torques or forces, which will then guide the dynamic system into a direction we want. At the same time, the interpreter will provide a logical input signal which changes the logical states of the plant. For instance, the sensor configuration here, or the actuator configuration, or the dynamics itself, if we are using the underlying feedback controller. Then the states will be measured here, so the measurement by Y will go into an estimator. This is important in real-world applications. We have to estimate our real system states. And if this estimation is finally part of the goal conditions, we are done, and if not, we apply a subsequence of actions C here and update the current hybrid system state, which goes into the planning problem again. And we start the whole loop again until we have found a state satisfying the goal conditions. We also did some feasibility analysis. We have here the task that we have to bring a small ball, a dynamic system with a position and a velocity, on this tilt table here to a state satisfying some goal conditions. So a small flag here. and therefore we can incline the plate around 2 axes, leading to 9 different plate inclinations, each having operation delta I of half a second. The holes here and the edges of the plate are simply modeled by preconditions, so we check in each state if we have fallen into a hole, and if not, we can continue with the planning process. We applied this problem and this domain to a planner to temporal fast downward, and let's see what the planner did. First of all, the planner found a solution. It's shown here, this thick black line guides the ball around the obstacles into the dome. And we see also the planned state, actually. These are the black dots. And we see another interesting thing. We see intermediate found promising trajectories that are trajectories that lead into a state which was good regarding the heuristic information of temporal fast downward. So temporal fast downward did not plan directly to the goal. We planned into a state which was good regarding the heuristic information, and we started going to that direction until we have found a state which is better regarding the heuristic information. It's this one, and we go further into that direction around this obstacle until we found a state which is even better than regarding the heuristic information, and then finally we could plan directly into the goal, thereby generating an input signal, a sequence of plate inclinations in time, by a planning algorithm. So this sequence of plate inclinations will lead this ball into the goal state. Let's discuss the approach. Our experience with domain predictive control showed that we first of all had to find a balance between the planner performance and the model accuracy. Of course, we would like to have fine-grained discretized actions in time, but this will heavily increase the plan length. At the other hand, of course, we would like to model each imaginable input fragment, but this will increase the number of available actions in each node of the decision graph. So the planner might fail to find a solution in such a huge decision tree. So I think the only thing we can do on the planning side here is to improve the heuristics, that we don't have to explore so many nodes before leading the current system into a direction which is good, into a correct direction. And if there's still an imbalance here and we don't find the solution in a reasonable time, we have to increase the computing power to increase the prediction horizon or to increase the number of explored nodes. I would like to end with a short summary of pros and cons. Let's start at the cons side. I think the most important issue here is that we have to anticipate our input fragments. That could be a very rough approximation of our real planned probabilities. Then we have a system dynamics, although the domain model is the discrete version of our real-world system. That means the planner has only knowledge of the actually planned states and no knowledge of the trajectory in between two planned states. There could lie an obstacle, so there are some validation issues rising here. The computation and effort is still quite high, and currently we can only cope with linear systems that are systems which we can model by the use of linear differential equations. But at the pro side, we have general problem formulation. We can apply this approach to a large number of problems. Then we can actively plan with system reconfigurations. We can handle restrictions in the state space, and we can at least try to increase the failure tolerance of systems by continuous replanning. Very briefly, a short outlook. We used this approach to predict or to generate plans that lead to acceleration profiles of landers to safely land at surfaces. Not only generating acceleration profiles, also generating a gain scheduling I don't want to go into detail here. If you're interested in this research, I will present this result on the Astrodynamic Specialist Conference this year in August with the title Planning-Based Autonomous Lander Control. Okay, what's the take-home message? With domain predictive control, we basically have realized a planning-based feedback loop generating an input signal here, which accounts for restrictions in the state space, which accounts for changing system configurations. We can even actively trigger system reconfigurations, which accounts for changes in the environment or in the system itself. And all in all, we are processing here a lot of more information than in a normal control feedback loop. And from our point of view, this is a quite interesting approach. Thank you very much.
Okay, questions? Oh gosh, what's the questions?
So around slide 19, I think you said something that sounds like it's going in the direction of what would be called tracking performance in tracking controllers. Mm-hmm. Do you think that concept might apply here for your domain predictive controller?
Actually, tracking a reference input, which also changes, could be difficult. Currently, we are only trying to achieve a constant set point in future. So we have not, no, we didn't work on this reference tracking up to now. But we are thinking about that, and this could be an issue in future work, I think. And so we are right at the beginning right now.
Yeah. In standard control theory, time discretization is crucial to ensure stability of the control. What about your approach to implement was how you discretize time? I mean, using control theory that we measure high or too low, difficult to choose the right time discretization.
Actually, yes. So the time discretization, we are doing a time discretization, it's true. And the actions even don't have to be discretized at the same time. Regarding stability, I think this was a question, right?
Yeah.
We have a predictive control approach. That means we are explicitly predicting future states. So we have knowledge of future states, and we can avoid to get into future states which are diverging, for instance. But the stability aspect is, of course, an important issue, and we will have some research on this in future work as well. Of course, it's a very good question.
Yes, Jonas, thanks for your talk. I had a question on slide 24, 23.
Okay.
You were displaying this trajectory that eventually you want to execute.
This one here?
Yeah, this one, exactly. And it seems to me there is some trajectory smoothing going on over there. So I was wondering how you can still guarantee that you're not falling into your hole after you've smoothed your trajectory.
Where do I have the trajectory smooth, actually?
Sorry?
Where?
Well, it seems that your trajectory is not point to point, right? It's like
yes, actually.
A second order information going on.
No, it's because we have a dynamic system. It's because we have a system which has a mass and a velocity. So we are acting with a force, and we predict really the future numerical state, which is true if we apply this force, and this is actually the trajectory which the system will go if the system has a linear behavior. So this is not an interpolation, it's really the trajectory which is gone by the system itself.
Okay, so you can still guarantee that this will still be, let's say, a safe trajectory?
Of course, we have the validation issue that if there are some obstacles in between two planned states, then of course we cannot guarantee that this is a safe trajectory. So this is of course an issue, because that we have only knowledge of the planned states. Yes. But we're not doing an interpolation or trajectory.
No reference interpolation.
Yes.
Okay.
Just a question about the scalability of your approach. So how many states can you deal with, and how long is the horizon you can?
For this approach, I think we had a prediction horizon of, I think, 10 actions in future, and we explored something about 2,000 nodes in each plane depth. So this is a dimension of this approach.
What's the total length of the solution?
The total length of solution is 38. So the plan has 38 plane steps, but they are computed step by step because we replan in each planning step.
I think that there is a strong assumption in your approach. You assume that you have a finite set of available actions.
Yes.
Right?
Yes.
And is this assumption not too restrictive?
You're totally right. This is a restrictive assumption. We just have a finite set of actions, and if we have if we have a system which could have continuous input signals, for instance, this would really be a rough approximation. But there are applications for that. For instance, in the maneuver-based control, we can in one action we can store a whole continuous maneuver. So we think that in this research area we could apply such an approach.
Okay, one last question, sir.
Every system's time utilization is an issue.
Yes.
I mean, if I take too far of a step to my right, I'll miss hitting the wall. So
Yes.
If there are zero, so detecting events when you take large steps is an issue, and I'm wondering if that's an issue when you do this utilization. So basically the problem is that you take very large steps.
Yes.
You miss completely the fact that the continuous space is crossing a particular threshold.
Yes, we could walk through an obstacle, for instance.
So
Yeah.
you can,
Yes.
so do you take that into consideration when you're picking your, obviously you want as coarse as prioritization as possible. And so is that it, or you're just choosing a fine enough that it's not an issue?
But currently, we just have action with this constant duration, and if there's an obstacle with exactly in between two plane states, then we will miss that, and we will walk through the obstacle, and this is of course not possible. So this is really an issue we are working on.
Okay, we do have time for one very last thing.
Yeah, very shortly, how does it compare with standard control theory approaches or even reinforcement learning approaches? Because they tackle the same kind of problems.
Can you say that? Repeat that, please.
How does your approach compare with control theory approaches or reinforcement learning?
Oh, this is a very open question. I think, of course, normal or classical control approaches are much faster, for instance. This is one thing. Model predictive control is faster currently, and I think the interesting thing here is that we can process some unusual behavior of the system. For instance, if we have a control signal where we want to make sure that we have a logical consistency, for instance, if we have to preheat a thruster before we can activate this thruster, we can do that directly by this approach. So this is an advantage, but of course it's difficult to compare this approach directly to classical control approach.
Okay, I have to stop there. Thank you very much. Okay, so our next talk is bandit-based planning and learning in continuous action Markov decision processes, presented by Ari Weinstein.
Yes, so I won't be talking about the learning aspect of this talk, but it is the deeper interest. Okay, so in terms of motivation, there are a lot of planning problems that we just heard that are fundamentally continuous, so often when we're controlling robots or doing a lot of other tasks. There are continuous actions and states that we have to deal with. On the other hand, a lot of the planning literature is concerned with dealing with domains that have discrete properties. So when this happens, a common approach is to discretize the continuous dimensions and then plan in that discretized domain. So this can be effective, but the problem is that it can be very wasteful in domains, especially ones that have a large number of dimensions because of the exponential load that you get in that situation. So in this talk, we're going to talk about efficient planning and continuous markup decision processes, and doing so natively without any sort of advanced predetermined discretization. So in terms of the overview, I'm going to talk about the discrete bandit problem, which is probably the most simple bandit problem that exists, and then the extension to the continuous setting. And from there, I'll go into markup decision process as well as how to turn bandit planner into a markup decision process planner. And then finally, I'll show parameters of the approach. Okay, so simplest planning problem that exists probably is called the KRM bandit. In this setting, the agent is presented with a small finite number of arms, and each arm has an associated distribution of rewards. And so what we're interested in is finding the optimal arm A star, which is the highest expected reward. So there are a few values that we're interested in is the time t, the action is taken at that time, and then the reward that was achieved at that time as well. So we refer to the regret as the difference between the reward that the agent achieved up to some point in time, difference between that and what it would have had if it had pulled the optimal arm at every time step. So in this setting, it turns out this simple equation, which is called UCB1, is optimal. It has a lot of regret that's logarithmic in time. And the way it works is it just pulls an arm that has maximum score, where the score is a combination of the observed reward value and this other term here, which is called the bias term, which just gives a bonus to arms that have been sampled less frequently than others. So and A is just the count of the amount of times that arm A has been sampled at time t. So that's what the discrete band setting is. So we can extend this setting to a continuum where there's not a finite set of k arms, but there's some infinite number of arms and there's some smoothness overall the expected rewards of arms that are nearby to each other. So commonly it's assumed to be Lipschitz or Holder or something like that. So the hierarchical optimization approach is one algorithm that's designed for use in the continuous bandit setting. So basically what it does is stochastic global optimization. So the way it works is that it starts with a root node that covers the entire action space, and it tries to make a decomposition of that space as time goes on. And as it does the decomposition, each node in that tree stores a value that estimates what the upper confidence bound on the reward for that region could be. So when it starts out, there's just a node, and it just takes some action. And after it takes an action, it splits the node into two, so we have two nodes that result from that. And from that point on, every time the algorithm is given the opportunity to take an action in the domain, it computes what's called a B value, which I'll discuss in the next slide. And then it just follows B values really from the root to some leaf. So on the last iteration of the algorithm, it could have started here and then taken a trajectory down to one of those leaves. So at every point that it takes a sample from the space, it bisects the leaf. So this picture on the right is if we present the algorithm with this bandit. So this is the set of arms that we can choose from, 0 to 1. Those arms have the associated reward between 0 and 1 with some noise added to it. This is a tree that's built in response. So this just represents the depth of the tree. And as you can see, what happens is sampling is done with very high density in the region of global maximum, of global optimum. And so this is good because it is achieving both good regret as well as a very high resolution estimate of the region that has the global optimum. Okay, so now I'm going to go into the actual math of how the B value is computed. Just like in UCB, there's a term that incorporates a mean value as well as some bias term for arms that haven't been sampled very often. In addition to that, there's another term which is just a volumetric bonus. So for each node in the tree, there's some bonus that corresponds to how large the region that covers. So what happens is that for each of the tree, we compute the upper confidence bound and then we recursively compute B. So B is a combination of two upper bound values. So it does is it takes the minimum of the two upper bounds that exist. And so this algorithm has optimal regret in this setting So this UCP is optimal growth, that's logarithmic at t, this is optimal growth, that's in square root of t. So now we're going to move to mark off decision processes. This is probably familiar to a lot of people, but it's defined as having a set of states S, a set of actions A, a transition distribution, so for every state action pair, there's a distribution over next states that can be arrived at. There's a deterministic reward function that maps to every state action pair to some real value, and then some discount factor gamma, which prioritizes immediate versus future reward. So in this setting, we're going to assume that A is infinitely large, because we're going to be planning for continuous action spaces, and we're actually making no assumptions on this. So it can be finite, it can be discrete, or it can be continuous, or it can be a combination there. So in the algorithm, we are going to try and maximize the expected discounted finite presence return, which is this equation here. So to do that, we're going to be using sample-based planning. So in this setting, we assume that the agent has access to a generative model. So how the generative model works is that the agent can pass any query state action pair, and in return it gets back a reward and next state, where the next state is sampled from the transition distribution. So the domain tells the agent some state S to plan from. The agent creates a general model with a large number of state action pairs, with whatever information it wants. And then after it does that, normally after some timeout occurs, the agent informs the domain of what action it thinks is the best action to take A, resulting in a new state S, and this loop repeats over again. Okay, so now the question is, we have an algorithm that's designed for planning continuous bandit settings, and how do we apply it to continuous MVPs? So the approach I'm going to talk about here is called hierarchical open loop optimistic planning. It was introduced and analyzed theoretically in 2010. It's never been demonstrated, the performance has never been demonstrated empirically. So it does, it casts the n-step planning problem as a large optimization problem. So if the original domain has one action dimension, and we're planning 10 steps, then it's an n-dimensional optimization problem. And if the original planning problem is 2 action dimensions, it's a 2 n-dimension optimization problem. The planning is done open loop. So what we're trying to do is get an association between a sequence of actions and this discounted return that I showed you before previously. So what we do is we use who to optimize the 10-step planning, and then we use the first recommended action, and then we start planning all over. So if we're doing one step look ahead in HOLON, we're just maximizing the immediate reward R1. And this is just a one-dimensional function that we're trying to optimize. And it's really equivalent to the bandit setting. So if we're doing this, we're not really doing anything special for any of these. But if we're doing 2 steps of look ahead, now we're trying to maximize R1 plus gamma R2, where R1 is the immediate reward we get, and R2 is the reward that we get at the following step. So here the horizontal axis represents the immediate action, and the vertical axis will represent the next action that we take in the sequence. And so we can keep doing this, we can keep generalizing this out. If we do 3 steps of look ahead, we're now trying to do optimization in 3-dimensional space. So what are the properties of the algorithm? So like who, HOLON improves at a rate of O squared of t. And this is independent of the action dimension and the depth that we're planning to. But this is only true as the number of queries that we're using becomes very, very large. So in most settings, those values do actually matter. On the other hand, because we're doing open loop control, it means that the algorithm is truly agnostic to state. So the size of state dimension and whether it's discrete, continuous, or hybrid doesn't matter at all. As an anytime planner, we can stop at any point and ask for what the best action it thinks it has, and the performance will continually improve as we give it more time. Finally, one negative thing is that because it's an open loop planner, it can have arbitrarily bad performance in domains of particular structures if they are noisy. So now I'm going to compare HOLON to UCT. So for those who aren't familiar, UCT is an algorithm that's become very popular over the past few years. It stands for upper confidence bounds applied to trees, and it is also a sample-based planning algorithm that uses results from bandit literature. So just as HOLON is an algorithm that's designed for continuous MVPs, UCT has UCP1 inside of it that controls the policy for finite MVPs. And just to point out that it is a very powerful algorithm, and it's considered state-of-the-art for a lot of areas, including planning and code. So the domains I'm going to show, they are continuous. So in order to leverage UCT in those domains, we have to use some coarse discretization over both state and action spaces. So the two domains that I'm going to show results for, they're sort of canonical control domains. One is called the double integrator domain, where we're controlling a point mass that starts at some position with no velocity, and we're trying to guide it to the origin where there's the position of velocity equal to 0 by controlling the acceleration. And the reward is negative sum squares the position and the acceleration that's applied. And the inverted pendulum, we're controlling actually a force at the base of the pendulum, and we want to prevent it from falling down. And the particular reward structure we use penalizes high magnitude actions, high angular velocities, and high angular momentum. So what we have here are the heat maps. They don't show up so well with the projector, unfortunately, for the two algorithms in two domains. So on the left are the results for the algorithms in the double integrator, and on the right is for the inverted pendulum. And for pull-out, we have one shade of color because there are no parameters to the algorithm. But with UCT, we're trying to find the best performance over a number of possible combinations of discretizations for the state and action. In the double integrator domain, the performance of pull-out was always statistically significantly better than UCT for all 49 different parameterizations we attempted. And in the inverted pendulum, there were 3 parameterizations of UCT that were not statistically significantly different, but all others were. So the punchline here is that if you use a planner that's designed natively for continuous settings, you can often get better results, and you can get better results with a small amount of parameters that have to be played with. Okay, so we're going to move on to conclusions. How am I tonight?
You're fine. You have 7 minutes.
7 minutes. Okay, so just to go over it again, pull-out is an effective continuous action planner. It's almost entirely parameter-free. If you make particular assumptions on if you know something about how the relationship between some arms works, then it's entirely parameter-free. And because it's parameter-free means that it's very easy to achieve good performance. The open loop control means that it functions agnostic to state, so you can use it very easily. And finally, although domains with some structures can cause problems for open loop planners, we didn't encounter this in practice. And we tested a lot more domains than the ones that we showed here. So just to cap off, because of poor generalization, algorithms such as UCT that are effective in discrete domains are not always effective in continuous domains because of the poor generalization that occurs when they're adapted out. And superior limitations.
Okay, questions? Yeah.
Have you considered to compare your method to motion planners that have been developed in continuous setting, for example, rapidly exploring random trees or other sampling-based approaches that are specifically designed for these continuous problems?
Right, so that's a very good question. So they're definitely coming close to each other, but I think one of the issues with a lot of motion planners is that they're just concerned with achieving some goal state. But they don't do so by minimizing some criteria in many cases.
In fact, there are some recent developments where there's been shown that they actually compute optimal paths. So, for example, RT star.
RT star, yeah. But you have to give it some cost function, I guess, associated. Yeah, it would be nice thing to do. I don't do that because my understanding is that a lot of them are just concerned with finding some cost. And they also need to know more things about the dynamics of the domain themselves. So that's one other constraint that they have. But there's certainly, for the settings they're designed for, that it's probably better to use things.
Okay, other questions?
I may have lost track, but is there still an assumption that you know how many steps you're going to have in the plan?
So you can assume how far the planning has to be. So if you tolerate a certain amount of error in the value that you're computing, you can say based on the bounds that I know in terms of what the value function could be because of the reward function, you can say I know I have to plan it most this far out. So if you say I'm going to accept 0.1 unit of error in my value function, and you know what the reward range is in the domain, you can compute how long you're planning out to.
Without knowing the dynamics?
Without knowing the dynamics, yeah. Because of the discount factor. If it wasn't discount, you know.
So you referred to ECT here, but there must be other algorithms as well in the RL literature. I think even by looking in co-authors that could also work here. So there are other algorithms aside from ECT here too. Can you speak to the comparison if you had done it?
Well, there aren't many other reinforcement learning planners for continuous action settings. There are actually very few that I'm aware of.
The multi-resolution. The citation there of the multi-resolution work.
Okay, so by looking in Nuremberg, so that's actually an algorithm that drives exploration. So that was for the learning component that's in the paper but not in the talk.
Okay.
There is a paper that I was actually co-authoring in ICAPS that was last year that's a continuous action planner, but the computational costs are extremely high, so we did run the comparison there. So it's basically, if this is like the unit cost, then that is unit cost time the depth of planning we're doing.
And Venus Moore in 2002 had a very sort of famous paper, continuous state actions.
Okay. Maybe I'm not aware of this.
Okay.
But in the paper itself, I do compare it to a lot of reinforcement learning algorithms, so not planning, but reinforcement learning algorithms.
Okay, that's
Through learning and living.
Okay, one last question. Okay, then let's thank the speaker.
Today I'd like to talk to you about three things. The first is this new, very interesting problem, waypoint allocation and motion planning. It's very interesting because it combines task planning and motion planning, and it's very similar to vehicle routing, but now you actually have to do the routing. It's not just a distance matrix. And to cope with this problem, we came up with an efficient solver that takes all sorts of ideas from classical planning literature, such as taboo search, line search, heuristic search, linear programming, and simple temporal networks to deal with this type of problem. Moreover, this problem is actually based on a real problem in industry that people are interested in, so that's always a fantastic thing. They came to us with their solution, some data about it, and we were able to use planning ideas and improve over theirs by 2.5 times in terms of speed and significantly more scalable than theirs. So, to motivate this problem, let's take a look at vehicle routing. Depicted here, we have a depot and a fleet of 3 vehicles, and the goal is to allocate these tasks to each of these vehicles and achieve the cheapest routing possible. These edges are given by a distance matrix in this problem specification, and associated with each of these points are temporal constraints. Motion planning is the goal, or is the task of combining a start configuration with an end configuration, trying to find a feasible trajectory to do that over a continuous space. Moreover, we need to respect the vehicle's dynamic limitations as well as avoiding obstacles while minimizing time for some cost function. Typically, it's time though. The natural combination of these two problems leads to our problem, waypoint allocation and motion planning. We have the same sort of main driving ideas. We're trying to allocate tasks to these vehicles, to the fleet of vehicles. We have temporal constraints on each of these tasks. We're looking for feasible trajectories through continuous space. So we're no longer relying on a distance matrix. We have to actually build those paths ourselves. We have obstacles we have to avoid. And we've we've had the specification of this varying traversal cost depicted here in red. And we're looking to minimize a linear combination of time and cost in these types of instances. So a more realistic sized instance is this one. So we're looking at more waypoints, just larger spaces in general, larger fleets. Description of these types of larger instances, we're looking to scale up to 16 aircraft with varying velocities and turning radius. So these are unique vehicles, not necessarily uniform across the fleet. We scale to 40 waypoints. Each of these waypoints have time windows, relative temporal constraints, as well as configuration constraints at that waypoint. So things like acceptable headings at those waypoints, as well as radii that you can achieve that waypoint in. We have also, as you saw, 40 radar sensitive zones, because this is actually a battle space management tool that we were working with. And these strict no-fly zones, so you cannot have any path intersect with those. Moreover, this problem is supposed to be integrated into a human in the loop, so we need situations. So we need to find solutions very quickly, and we're looking for 7 seconds as a strict time limit so that we can be interactive. So we have vehicle routing and we have motion planning. These are very common problems, and for the most part we have great solutions to them. So why is putting them together so difficult? Well, when we think about it and we try to break this problem down to build a solution, well, we can't do the task allocation without knowing the routing costs. And we need the cost from one waypoint to the next. And if we don't know the cost, if we can't find the routing costs without the motion paths. The motion paths are what is actually going to drive the cost function. And we can't find the motion paths without knowing the leg durations. This is a very subtle point because we don't know how much time we're able to allocate to each of these legs between waypoints. So we can't figure out if there's enough time to avoid high-cost areas. And we can't assign these leg durations without this idea of a time-cost trade-off. So which legs can we provide more time to that will benefit from this additional time and cost reduction? This may be a little unclear, so I have a very simple example that I'm going to walk through. On the top left here, we see that we are, this small simple instance where we have a vehicle here, one waypoint and another, and it's being blocked by these two cost areas. In this case, we see the fastest path between these is obviously going to be the straight line path between them. But this could be very expensive, obviously. The other alternative is the cheapest route. But this could be too long given the temporal constraints. So using this bit of information, that is the fastest route between these 2 points, between this on this leg, and the cheapest path on this leg, we assume that we can interpolate between these. So by giving more time to this leg on the overall solution, we're able to reduce the cost like this. And you can see here that by giving more time to this leg, we're able to reduce the cost over time, but not as quickly as here in this more expensive area. So this is our approach. First, we have a pre-computation step, which is tasked with finding these linear interpolations of cost-time trade-off. They're going to pass that along to the sequencer, which is going to allocate and assign an order to these waypoints to each vehicle. That ordering then propagates to a linear program that we've set up to assign actual time points to the waypoints in the form of a timetable. The timetable then is passed to the router, which is tasked with finding motion paths that connect the waypoints given the timetable in the time they've been allocated. However, if you are paying close attention, we were estimating the ability of the router at this high level so we could avoid high computation motion planning. So we have the idea of feedback at the bottom. So if we were given a timetable that we just can't achieve at the routing level, we'll pass this information back up to the linear program where we'll deal with it in the form of new constraints in the linear program. So let's look at this a little more in depth. So the pre-computation phase is very simple. We're going to discretize the space and we're going to find the shortest path between the waypoints, all the waypoints, as well as the cheapest path between all waypoints. So we get these 2 endpoints on our line of interpolation. So we're going to take this circuit objective, as I'll call it, and we're going to pass that on to the sequencer. The sequencer is actually a local search technique using taboo search, and we will keep track of a simple temporal network to maintain temporal feasibility. So we'll find a simple ordering of the waypoints, allocation and task allocation to vehicles, as well as the ordering of the waypoints. So just simply the order. So waypoint 2 will come before waypoint 3 and will come before waypoint 1. These partitions and orderings are then passed on to the linear program that we've set up. The linear program will take the circuit objective as well as this feasible ordering and will solve this problem such that we minimize a linear combination of the cost and time. That's a user specification that they can provide to do that, the trade-off of cost and time. These, each leg of the plan will then be assigned a time point given the output of this, such as waypoint 2 should be achieved by, at time 2, waypoint 3 should be achieved at time 3, waypoint 1 should be achieved at time 5. This timetable then gets passed on to the router, as I hinted at earlier, where we will try to instantiate this timetable with actual motion plans that get between these waypoints. We do this by using a discretized A-star search over location and time. And then we use a pre-processing smoother to get rid of some of these dynamically infeasible terms. So, as I said, the discretized A-star search between the waypoints, we have a temporal pruning now given the timetable. So, if we have the S, we can do temporal pruning if the time from the start to the node we're currently at, plus an estimate of the time remaining exceeds the timetable value that we were provided, we can just prune that search branch. Also, because we have this kind of pruning, we may need to re-expand nodes. More specifically, we may have to expand nodes that are more expensive so long as we arrive earlier to that node. So here we can see we are avoiding cost here in a very cheap way around the edge, but when we get to this point, we realize that the remaining path will be too long and we won't be able to achieve that waypoint in time. So we have to explore more of this path at a more costly, more cost, until we finally can find a path from the start to the waypoint, respecting the upper bound on the time. And here we can see that we'll have to re-expand this node here at a higher cost, but an earlier time to achieve this. Also, because of the smoothing step that I'll talk about in just a minute, we keep this A-star search presumable. Just really means that we keep the open list and the closed list around, so we can continue the search if we need to. And this is exactly why. So the result of that step is just these very jagged paths that are not flyable by any aircraft that I really know of. So we apply a smoother over these. But by smoothing, we can actually increase the length of the path that we found. And by doing that, we may no longer make that timetable value, and then we can no longer continue with this plan. But there's hope. We can take this information of what we've just done and post a new constraint to the linear program. The linear program will then take that new constraint and try to resolve and assign a new timetable to the waypoints. If it's the case that we've added a constraint that makes this ordering and partitioning infeasible, so the LP cannot solve it, we'll pass that information back to the sequencer and we'll basically start from the beginning. So that's a lot, but how does it do? Well, first of all, we did kind of an initial look at the problem where we did a unified A-star search. So we're keeping track in the state of X, Y, theta, and time. These are very simple problems, no temporal constraints. We have a pretty good heuristic. We'll give it as much time as it wants and bounded memory of about 7.5 gigs. This table here shows the number of waypoints in the instances as well as the failure rate of this simplified approach. And you can see as we scale up the number of waypoints, we get to complete failure, and that simply will not do. So this generic A-star search just was not going to do it for us. But we have a complicated system, and it makes sense to try to test the individual pieces rather than the whole first to make sure that everything is working. Just a general debugging kind of thing. So we took a look at the sequencer, and we constructed these TSP-like instances to test the ability of the sequencer to find good orderings among these waypoints. We constructed these as a problem with a single vehicle, epsilon turn radius, no temporal constraints, and we've spread a uniform cost with no keep-out zones across the entire map. So pretty much a standard TSP, but we'll have to actually route. But epsilon turn radius means we can pretty much connect straight lines. We sent these off, and we were able to calculate optimal solutions as a baseline. And M and G represent two instantiations of our system. I refer you to the paper for more information about those. And also just a naive nearest neighbor TSP solver. So we have the factor of optimal on the y-axis and a little bit of scaling on the x-axis. So this first box here is 40 tasks, and we do pretty well, about a little more than 1.2 more than optimal. And as you see, as we scale up to 100 tasks, we pretty much stay around there. So we say that the sequencer is finding pretty good orderings, and we can trust that in the long run. The next component of this is the router. So to test this, we created these intricate, high-cost mazes. And it's a single vehicle. It has a small turning radius, not necessarily epsilon, but small. And there are no temporal constraints. We know that the router is capable of finding good, we know that the sequencer now is capable of finding good orderings, so we can rely on that. But can the router get through these types of instances? And this small example, I think, is a pretty good example of, yes, it can. We also scale up to much larger mazes, but if I put it on the slide, no one will be able to read it. So the router works well. But how does it perform in practice? How are the realistic instances that we were initially concerned with? So here we have 3 instantiations of the algorithm. Again, please look at the paper for a better real description. But we see the y-axis, we have final solution cost and the total wall time. Here we're trying to test the scaling of number of waypoints in these instances. We hold the number of vehicles constant at 4, and as we scale from 10 to 20 to 30 to 40 waypoints in these instances, we are well within our bounds. So we scale very well with the number of waypoints. The next part is the number of vehicles. So for these instances, we have held the number of waypoints constant, and now we're just scaling the number of vehicles. And you see in this very confusing cluster, there's about 1 and a 4, and then we come up to 8, and the progression is more clear, up to 16. And again, we're still well within the bound of our industrial partners' expectations. So we scale well, as I mentioned earlier. So, what's the big picture here? Well, we have this new problem that is incredibly fascinating to work on. It's combining, like I said, task and motion planning, a very easy to understand problem, a great comparison, dare I say benchmark, maybe not, but just a great way to compare work and share ideas. Like I said, it's vehicle routing with real routing, so it's a little more realistic than the OR version, but that's okay. We have this efficient solver that, like I said, is using ideas from all sorts of planning topics. So these are not the only ones. You can stick things in and try things out. There's just so many great ideas that you can explore in this. We found this combination actually worked very well for us in the context we were interested in. And as I said, this meets the application requirements. We're able to surpass the industrial partner's initial solver by 2.5 times in speed, as well as being much more scalable than they were. So thank you.
So I take it there are no implicit dependencies implicit constraints between your vehicles. For instance, collisions are not possible. They're all flying vehicles on the canal, right?
Correct.
And I have another question regarding the type of vehicles. I suppose you have some kind of kinematic model of the vehicle. Or are you ignoring the kinematic feasibility of the motions in your A-star? Or are you actually coming up with kinematically feasible paths or trajectories into that?
Okay. It's actually a very simple motion model. The industrial partner was specifically concerned with constant velocity, so we were able to just use Newton's paths as the final solution. However, the A-star search, as you asked, is infeasible. It is over a grid solution, so like I said, it's those jagged things, but then we run the smoother over at the end to do that. Does that answer your question?
Okay, there's a question behind.
Yeah, I was wondering, the vehicle riding problem you often see, at least in the OR field, large neighborhood search or this sort of randomized decomposition approaches. I was wondering if you maybe tried these and found out if yours works better, or if you want to try them.
I don't believe we tried them. I think we found that across the literature, taboo search seemed to be pretty popular. We're not OR guys, unfortunately, and we kind of just did a good looking, and taboo search seemed to be popular. And as I said, it worked very well for us. But yes, that would be a wonderful exploration further into the problem.
Okay, thank you. Any question?
So I was going to ask, it seems that when you're doing the smoothing and you're using that to pose constraints back to the linear program, that it's possible that you're over-constraining the linear program, because it might be that there were alternative routes from the A-star search that would have smoothed to achieve that final solution.
That's very true. We don't really take that into account. We were starting to work towards that. It gets very, not that it's an excuse, but it gets very complicated trying to anticipate for the smoothing. We do, however, try to do the smoothing the best that we can. We have this idea of first minimizing the cost during smoothing, and if the cost, if the minimized cost solution after smoothing is too long, we do try to scale it back and try to come up with a shorter solution. We don't do any sort of anticipatory search in A-star to find a more smoothable solution. But that's very interesting.
I was wondering whether you should postpone posting constraints back to the linear program until after you confirmed that other A-star, other solutions in the A-star queue were not going to smooth to the...
I apologize, didn't make that clear, I think. So the A-star search is resumable.
Yeah.
If we find a solution that gets smoothed and is too long, as you said, we do have that entire open list of possible solutions that are much shorter. So we will, before falling back to the LP with a new constraint, we will exhaust the open list until we've pruned everything.
Okay, do we have another question? Yeah.
So, two quick questions. After you do the sequencing, you have independent problems for all your vehicles, so are you solving them all independently?
Yes.
The second question is, there's a problem decomposition framework that's being used a lot in CPU scheduling called logic-based vendors decomposition. It has exactly this pattern of sending back cuts and resolving math problems, and it looks a lot like a two-level logic-based vendors decomposition. So I was wondering if you were aware of that work and comment on it.
I've heard that phrase and it's always impressed me, but I have no idea what logic-based vendor decomposition is, so I'm delighted that we rediscovered it.
Okay, there was a question over here, Jeff.
Yeah, so you said you used surrogate objective. What did you use exactly for that?
A linear interpolation between the time and cost of the fastest path that we can get between between all pairs of waypoints with the endpoint of the cheapest path's time and cost. So we assume that by adding more time to this, we'll be able to decrease the overall cost. So it's just a linear interpolation between those 2 points.
Okay, do we have any further questions? Okay, then let's thank the speaker. I'd like to just, before we finish the session, I'd just like to remark that we had another paper in this session which has been moved into the best papers track, and that will be the temporal planning of preferences and time-dependent continuous costs by Jay Benton, Andrew Coles and Amanda Coles. So please go along to see that best paper presentation tomorrow. Okay, thank you very much everybody for attending this track. I hope you found it interesting. It's been very good. 3 very nice papers. Thanks guys. And now we'll break for coffee.